Hello everyone, this is the first video of the GGM YouTube channel where we will be doing mathematics, which will be mostly centered around AMC 8 to AMC 10 difficulty mathematics. This channel is aimed at exposing more kids to competitive mathematics and to allow higher understanding of both mathematics and problem solving as a whole. So this week we will be doing Intro to Counting, which is basically an introduction to combinatorics and probability, which are two prominent concepts in math competitions. So this is going to be a basic overview of combinatorics, and next week we'll have more advanced combinatorics techniques. But for this week it will just be more simple stuff that perhaps people can get a better grasp on. What is combinatorics or counting? So in contests like the AMC 8, AMC 10, or math counts, combinatorics usually refers to the number of ways to count something. So here's an example. How many ways are there to reorder a red ball, a green ball, and a blue ball in a line? Right? So we're trying to count how many arrangements of the red, green, and blue balls there are. And you might be saying, well, I can just count them straight up, right? I can just say, well, there's red, green, blue, there's red, blue, green, green, blue, red, and yeah, it's true. This way you can cycle through all the possible arrangements, but the fact is, there's many different arrangements when you get to larger problems. What if we have 5 balls, 7 balls? Then you're going to need to use special combinatorics techniques. Then it gets very hard to use regular counting to count arrangements. So when we do counting problems, right, we're often looking for the number of distinct or different arrangements of something. So for example, let's say that Sharon has a green shirt, a blue shirt, and an orange shirt. So let's say she also has trousers, jeans, shorts, and sweatpants. How many different ways can she choose a shirt and pants? So, for example, a black shirt and a pair of jeans would be different from a blue shirt and a pair of trousers. Or a blue shirt and a pair of trousers, that's different from a blue shirt and sweatpants, right? So, how are we going to approach this problem? I'll give you 5 seconds if you want to pause the video. Okay, so the answer, I think you might have gotten it pretty easily. There are 3 types of shirts and there's 4 types of pants. So we simply multiply the number of shirts by the number of pants. So for each shirt type, we have 4 different types of pants. So we get 4 times 3 is 12 different arrangements. So to better understand why this is the right answer, let's use a visualization. So as we can see, for each of these 3 different shirts, we have this shirt up here and these 3 shirts here. And each of these are going to have 4 pants, right? So each of these has a different arrangement, right? Your starting shirt will always produce a different arrangement. And then from there, you have 4 different pants. So it's 3 times 4. Or, you know, we could have done 4 circles, and then each of those circles have 3 squares. You know, it's really the same thing. So I think maybe you have the hang of this type of problem by now. So let's extend this previous problem just a little bit. So let's say she has her clothes from before, but she also has 2 different types of hats and 4 different types of socks. So now with her 3 shirts, 4 pants, 2 hats, and 4 socks, how many different outfits can she choose? So just giving you 5 seconds for that one. Pause the video if you want. So the answer, I think you might have guessed, is just to simply multiply all of these together. So remember, for each of her 3 different shirts, she can choose 1 of 4 different pants. And then for each of those 12 possibilities, these are all 12 different arrangements, she can choose 1 of 2 different hats. So 12 of those are with 1 hat, and then 12 of those are with the other hat. So that's 12 times 2. And then for each of those possibilities, she can choose one of 4 socks, right? And it's the same thing, right? For 3 times 4 times 2 possibilities, well, she can choose the first sock. And then for another 3 times 4 times 2 possibilities, she can choose the second sock, and so on, right? So the total number is just, you just multiply them all. It's 3 times 4 times 2 times 4, and that's 96. And another one, so Dan is about to take a test. He has 9 pencils and 3 erasers. He may only choose 1 pencil and 1 eraser. So how many pencil eraser combinations are possible? You might figure this one out as well. So it's very similar to our first problem. So for each of 9 pencils, he can choose 1 of 3 erasers. So the answer would be 9 times 3 is 27. So make sure you understand this concept of for each of the 9 pencils, he can choose 1 of 3 erasers, right? For each pencil, you can choose the first, the second, or the third eraser. And because there's 9 different possible starting pencils, we have 9 times 3. So now that we know how to count arrangements, we can start talking about another aspect of counting, combinations and permutations. So combinations are a way of counting items from a collection where the order of items does not matter, okay? Does not matter. So if you take a combination of items and rearrange them, they are still considered the same. And we'll get into this a little bit more later on, but permutations are a way of counting items from a collection where the order of items does matter. So if you take a permutation of items and rearrange them, the result will probably be different from your original permutation. Right? So, for example, let's say I'm ordering some food at a restaurant, right? So if I'm ordering food, I don't care about the order of the food items, right? I care about what food items I'm getting, right? So if I order, let's say, a soup, and then a salad, and then maybe a main course, right? I don't care if I get the salad first or I get the soup first. Well, some people might care, but let's just say we don't. I don't really care about the order of the food items. I just care about which ones I'm getting. So because the order does not matter, that's an example of a combination. But, for things like phone numbers, this is totally different, right? So the order of the numbers is going to matter a lot. So even though I have the exact same numbers in this first phone number, it is a completely different phone number from the second phone number. So that's the difference between combinations and permutations. And the interesting thing is that a combination lock actually utilizes permutations of numbers. So I'm not sure if any of you have ever really used a combination lock, but you know that if you put a certain permutation of numbers in the lock, it's gonna, for example, you have to put them in a certain order, right? So if the lock wants me to do 473, for example, if I do 347, it's not gonna work, right? I mean, it's the same numbers. It has 4, it has 3, it has 7, it should work. But it doesn't because the order matters, right? If it's a combination, the order shouldn't matter, but it does. So it should be called a permutation lock. And I think a lot of people have touched on this before, but it needs to be called a permutation lock. That's the accurate way of saying it because the order matters. Okay, so here's another example of the difference. So let's say Sharon, she wants to take her 3 different shirts out for ironing, okay? So how many combinations of 2 shirts can she take? Well, she can take the green and blue shirt, the blue and orange shirt, or the green and orange shirt. So in total, there's 3 combinations of 2 shirts. And let's say she wears one of her shirts, and then she wants to hang the other 2 on the wall for some, like she's gonna wear them later. I don't know, right? So how many permutations of 2 shirts can she hang? Well, she can hang all of our previous combinations, right? Green and blue, blue and orange, green and orange. But she can also switch the order of each shirt. I don't know. Maybe she wants other people to see her style. Who knows, right? Maybe she wants them to see the blue one first, so she can have green and blue or blue and green, for example. So actually, for each of these 3 combinations, there are 2 permutations. So the answer is 6 permutations. But yeah, so as I was saying, um, let's say, I don't know, I have 5 shirts, okay, so, or, yeah, let's just say I have 5 shirts, okay. So now, let's just say I have S1, S2, S3, S4, and S5. Okay, let's say I want to find how many, or let's do 4 shirts, just for ease of use right now. So 4 shirts. And I want to find how many combinations of 4 shirts there are. Right? So let's say I want to find how many combinations of 2 shirts out of these 4. I want to find how many combinations of 2 shirts out of these 4. So I can choose S1, S2, so that's one combination. I can choose S1 and S3. I can choose S1 and S4, and I think we've gone through all the ones that just use S1, so let's do something else. S2, so we've already done S2 and S1, so let's do S2 and S3. And S2 and S4. And for S3, we've already covered it being with 1 and it being with 2, right? So the only really remaining one is we have S3 and S4, right? And then there's nothing left after that. So, because we've already covered all the ones with S4. So now we're done. So as you can see, we have 6 combinations, right? So we have 6 combinations. But, right, for each of these combinations, we have 2 permutations. Because we can have S1, S2, we could have S2, S1 as well, because now the order matters, right? So in combinations, these two are the same thing, but in permutations, they're different. So that's the difference between combinations and permutations. So if we just reverse all of them, I'm not going to write out the whole thing for reversing, but I think you can see that if we continue this onward, we're just going to have 2 permutations for every combination. So there's just 12 permutations. So let's try to solve the problem that we looked at in the first slide. So how many ways are there to reorder a red ball, a green ball, and a blue ball in a line? So this problem is really not that different from the how many different outfits you can choose problems we looked at before. So you should probably try to think about it in terms of positions. So how many possibilities are there for the first ball? How many for the second ball, and so on. So just take 5 seconds and pause the video if you want to solve it. So the key to solving this problem is you have to notice that you have 3 choices for the first ball, 2 choices for the second, and 1 for the last. So the first ball can be red, green, or blue, so that's 3 possibilities. And then whatever you choose for the first ball, the second ball only has 2 choices, because you can't just repeat the green, right? Because you only have 1 green ball. So the second ball only has 2 choices, right? Let's say you chose green for the first one, so now the second one can be red or blue. So if we choose blue for that, then the last one has to be red, right? So that's just 3 times 2 times 1 is equal to 6 possibilities. And if you got 3 times 3 times 3 equals 27, that's fine. This is a mistake that happens a lot. So the important thing is that you have to remember that once you place a ball, that possibility is now gone, right? So if I place the green ball, that's 3, right? It could be red, green, or blue. But then for the next ball, I don't have 3 possibilities anymore because I already placed one of those balls. So now there's only 2 left. So if I take this problem, for example, if I have an unlimited number of red balls, green balls, and blue balls, then how many permutations of 3 balls? Well, we can have red, green, or blue for the first, second, and third because we don't have a limit to our number of balls. So that would be 3 times 3 times 3 is 27. So if a problem says with replacement, repetition is usually allowed. But if it uses words like, sorry, it's always allowed. Yeah, if it says with replacement, that is your go-to for determining whether repetition is allowed. But if it uses words like without replacement, repetition is not allowed. So for this lesson, we'll just be discussing problems without repetition, which is problems where the final result has items that are all distinct. All of them are different from each other. So we can't have 2 red balls or 2 green balls or something. So the answer has to have all distinct parts, right, if repetition is allowed. So there can be more than one of the same item in the problem, but if the answer can't have duplicates, it is without repetition. So let's just extend the problem in the first slide. So if there's 5 distinct balls instead of 3, try to find the number of permutations. So do you start to notice some sort of pattern? I'll give you 5 seconds. So I think this is probably similar to what we've done before. So answer is just 5 times 4 times 3 times 2 times 1 is 120. So there's 5 possibilities for the first ball, 4 for the second, and so on. Right? So it's clear that the numbers we're multiplying keep going down by 1. So it's called a factorial, and it's denoted by an exclamation mark. So if I put 5 factorial, what I'm really saying is 5 times 4 times 3 times 2 times 1. And then 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. And in general, you're going to have n factorial equals n times n minus 1 times n minus 2. And it just multiplies all the way until you get down to 1. And now I think we're ready to go to the permutation formula. So the permutation formula, you often write it as NPR. And n is the total number of items, and r is the number of items we're choosing. So if this gets tricky, just try to hang on. I promise this will make sense in a moment. So this formula only works for no repetition. But if it doesn't, AMC 8 problems usually will not have repetition. AMC 10 will. But if it doesn't say which, you should probably assume without. So what is the permutation formula? So let's say that out of our 5 balls, we want to see how many permutations of 3 balls there are. We have 5 choices for the first, 4 choices for the second, 3 for the third, and then we're done, right? Because we only want 3 balls. So we only take the first 3 numbers of 5 factorial. So if we have n balls, we only take the first r numbers of n and multiply them. Of n factorial, sorry. So the permutation formula is NPR is equal to n factorial divided by n minus r factorial. And the intuitive way to look at this is to see that when we are dividing n factorial by n minus r factorial, we remove everything except the first r terms of n. So we can have NPR is equal to n factorial divided by n minus 1 factorial. N minus r factorial, sorry. Remember, n is the total number of items and r is the number of items we're choosing. Right? That's how many items we want to find the permutation of. And a way to see this is you have n factorial, and this is equal to n times n minus 1 times n minus 2. And this is going to go all the way until n minus r plus 1. And then this is, we're going to keep going, right? N minus r, n minus r minus 1. Sorry. This is n, so. And we're all going to go down to But now the funny thing to notice here is that this whole thing, this entire block, this is just equal to n minus r factorial. So when we take n factorial and we divide it by n minus r factorial, what we're really doing is we're just, the result is going to be n times n minus 1 times n minus 2, and then we're all going to go down to n minus r plus 1. And as you can see, there are r numbers here. This is the first r numbers of n factorial. So all we're really doing is, and I hope this makes sense, because if we have 5 balls out of 5, there's 5 factorial ways. But if we have 3 balls, right, out of 5 balls, and we want to find permutations, we have 5 choices for the first, 4 choices for the next, and then 3 choices. And then we're done. So there's, in this case, n equals 5, and r is equal to 3. And then, as you can see, we have r equals 3 numbers, right? And these are the first 3 numbers of 5 factorial. So combinations, unlike permutations, will not take order into account. So in a combination, 1, 2, 3 is the same thing as 3, 2, 1. So, but the thing is, they tend to be harder to calculate a little bit. So as you can see, green, blue, same as blue, green in combinations, because order does not matter. So the way we calculate combinations is this. We assume that order matters, and then reduce it so that it doesn't matter. So let's go back to our ball example. So we want to find how many combinations of 3 balls out of 5 distinct balls there are, let's say. Not permutations. So just as before, we have 5 choices for the first, 4 for the second, and 3 for the third. This is the number of permutations, which is 60. But for each permutation of 3 balls, there are 3 factorial equals 6 ways to order them. And order does not matter in combinations, so we divide 60 by 6 to get 10, and that's our answer. So overall, we're going to take NPR and divide by r factorial to get NCR, the combination formula, and also known as the choose formula. We have our permutation formula, which is n factorial over n minus r factorial. But now, because there's r factorial ways to order r items, we have to divide by r factorial because we don't want the order. So we're overcounting by a factor of r factorial. So this is what NCR is. This is the number of combinations for n total items and r items that we are choosing. And this is also written as this. So with the n on top, I think somebody said it was almost like it was floating on top of the r, so that's another way to look at it. The reason the combination formula is called the choose formula is because it is the number of ways to choose r objects from n total distinct objects. So for instance, if we have 7 distinct boxes and we want to choose 3 of them, we simply do 7C3. And if you want to calculate that, I'll give you 5 seconds to pause the video. So we would have 7 choose 3 like this. Well, this is a notation that you will see a lot. And this is equal to 7 factorial divided by 7 minus 3 factorial, because we're choosing 3 items out of 7, times 3 factorial. So 7 factorial, this is equal to 7 factorial over 4 factorial times 3 factorial. And this is just equal to, well, 7 factorial divided by 4 factorial, that's just 7 times 6 times 5. And we want to divide that by 3 factorial. So the 3 and the 2 will cancel out with the 6, so this is just equal to 35. So n choose r is equal to n choose n minus r. So this can be derived algebraically because n minus r is equal to r, right? But another way to look at it would be that the number of ways to choose R objects from N objects is the same as the number of ways to not choose N minus R objects from N objects. So it's really the same thing. And the choose formula might look complicated, right? So an easier and equivalent way to find the number of ways is to choose R from N is to just multiply numbers of N until you have multiplied R numbers. Then simply divide by R factorial. So if you need to, think about why it's the same. But so for example, we have 10 choose 3. That's just 10 times 9 times 8. So we've reached 3 numbers, so we stopped. And then we divide by 3 factorial. So that's 120. And 0 factorial is a very interesting case. So the idea of a factorial is to find the total number of permutations of a set of length n, right? So if we have n distinct balls, we will have n times n minus 1 times all the way to n factorial ways for the total number of permutations, because we have n possibilities for the first ball, n minus 1 for the second, and so on. But there's only one way to rearrange a set with no objects, which is just the set itself. So 0 factorial equals 1. And next week we'll be going over combinations and permutations without repetition. And we will also be doing some problem solving techniques like complementary counting and stars and bars. So I'm glad that you joined us for this video today, and I hope to see you next week. Goodbye.